Okay, so key facts. You can't do anything else unless we have this securely in our grasp. That a sequence is what? You've been working on these, right? So with the last 2 days, 2 days of class, we worked on these sequences, right? We see there's a pattern, there's a formula sometimes, and the formula tells you what all the terms of the sequence are. And then we also analyze them for whether they converge or not, meaning as you march down the list, do those numbers get closer and closer to a particular value? And then as close as you want. So pick any amount of closeness. Does it eventually get within that amount of closeness forever? Okay, and then pick a smaller amount of closeness. Does it eventually get within that? That's what it means for a sequence to converge. For any degree of closeness that you want to this limiting value, the sequence will eventually get within that. All right, anything else in terms of the list is divergent. If it bounces around, if it goes to positive infinity, the numbers get really big. If they get really big negative, okay? So we talked about that. And then, so now we're going to talk about a series. Who remembers what a series is? Right, you take a sequence and you do what? You add them all together. That's what a series is. You take all the elements of a sequence and you add them up. And you add them up. Again, if you're not 100% solid with these terms, then everything we're doing is futile. Okay? So first and foremost, the sequence is the list, the series is the sum of that list. Okay, so if we got a sequence AN, then the associated series is, so if it means adding up all the terms of the sequence, what would we write? What would it be? No, just literally. Forget that you know the sum thing. Literally, what would it be? What did we just say? It's the sum of all the terms. What are the terms? A1 plus A, is that what you're going to say? A1 plus A2 plus A3 plus A4 plus on and on and on. Okay? That's what it is, right? So instead of just the list with commas, it's actually now we're taking them, we're adding them together. Okay? And then some of you mentioned summation, right? Summation notation. So rather than, because we have a formula often for the sequence, we can use summation notation so we don't have to write it this way. But this is always the way we think about it. We always think about it like this. That we're adding up the terms of a sequence. It's just we have a shorthand notation for it. Okay? The shorthand notation is, this thing is Greek sigma, stands for sum. And so this tells us we're going to start with n equals 1 and just keep going on and on and on. And these are going to be whole values, right? Whole values, just like they were with a sequence. Why do we start with a equals 1? Or why do we start with n equals 1? So that the number n tells us which number in the sequence that it is, or in the sum. Right? So we know that when n equals 4, that's the fourth term of the sequence and the fourth thing we're going to add. Right? Okay, so these are synonymous. Okay? So whenever you see this, you'll see lots of these. Right? What? Immediately, this is in your brain. Think this. No, because it's a sum. It's just a sum. Yeah. We're adding it up. Okay. I already have that programmed in. All right. This is crucially important because we're going to get into these complicated problems where we've got lots of steps and lots of symbols to move around, and we'll often be dealing with this kind of thing. So you can't lose sight that what we're actually doing, because having a firm, image that it's this is going to help us to solve the problems related to having that notation over there on the left. Okay. Okay. So here's a sequence. 2n minus 1. We've talked about that one before. So I want you to write out literally what that would mean. Literally, what would that mean for this particular sequence, 2n minus 1? Okay, so Monday I'm going to have my list of names. My list of names of you guys, and we're just going to be calling you out randomly. But today, I'll go by colors of shirts and other apparel. Okay, so how about Ori? I know your name. Ori, how'd it go? What does this mean? He said 1 plus 3 plus 5 plus 7. Agree? That's exactly what it is. Okay? So you could do that, and then you can substitute instead of a sub n, so it's this the sum of the sequence 2n minus 1, 1 plus 3 plus 5 plus 7 plus 9. Tell me about the sum. Pretty easy to see what's going to happen with this sum. It's going to be big, right? As big as you want, right? Pick any number. As long as you have enough terms of this sum, you're going to get to that number, right? You're going to get to that number. It's just going to get really big. Okay? So that's what we call a divergent series. So we had convergent and divergent sequences. Likewise, we're going to have a convergent and divergent series. So this is divergent since that sum is virtually infinite, right? Virtually infinite. There's no number you can pick where the sum won't eventually surpass it, right? There's no large number you could pick where you could take n large enough you could eventually surpass that number. So that's divergent. Okay? How about this one? 1 over 2 to the n. What kind of sequence is that? What kind of sequence is that? P sequence? Some are saying yes, some are saying no. Is it a P sequence? No, geometric. So what's the difference? Remember, a P sequence, that n is in the base, like a polynomial, right? But in the denominator, right? So the P sequence is when the n is in the base raised to some constant power. What is this the same as? How could we rewrite this? 1/2 to the n. And what is that? What kind of sequence is that? Geometric sequence. Geometric is when you have some constant number raised to the n. Got it? So if you're shaky on this, learn it quick, because we're going to see this over and over again. A P sequence is 1 over n to some power, like a constant power, like 1 over n to the 4th, or 1 over n to the 0.3. The geometric sequence is your constant is the base, and your exponent is n. That's your geometric sequence. Like an exponential function. Exponential function. Okay? So, write out literally what that is. Go. What does that mean? How about here? Black shirt and headphones. What'd you say? What is this? How would you describe what that is?
It would be the sum of 1
Okay, and what's that?
1/2 plus 1/4 plus 1/8.
He's saying 1/2 plus 1/4 plus 1/8 plus 1/16. Some people are nodding. That's right. Make sense? Okay, so this is it's like the turtle that's crossing the hallway in your dorm, right? Everyone has a turtle crossing the hallway in your dorm or your apartment building, right? You all seen the turtle, right? Going to the, you got to avoid it when you're walking down the hall, right? Okay, so I'm just kidding. All right. So it's just like, so here's the hallway, right? And wish that turtle would get out of my way. All right, so the first day, the turtle, walks halfway across the hall. So he starts day 0. The first day, he walks halfway across the hall, day 1. That crazy turtle. Second day, he walks another quarter of the width of the hall. Where does he end up then? 3/4 of the way across, right? So he's going to walk a half of the distance of the hall, and then he's going to walk a quarter, which puts him 3/4 of the way across. And the next day, he's going to walk 1/8 of that width, and where does that put him? 7/8 of the way across, right? And then the next day, he's going to walk 1/16 of the width of the hall, and that puts him at 15/16. So by doing this, every day he's walking half the remaining distance. Every day he walks half of the remaining distance to get to the other side. And that is a straight hall wall. It's important. Yep. Every day, half the remaining distance. Does he ever make it? Will this turtle ever leave the hallway? Does he ever make it to the other side? Yes or no? Okay, well, here's the key. We never run out of ends. What does that mean? Does the sum ever end? Okay, so if you picked any distance from the wall, is he eventually going to get that close to the wall? As long as your n is big enough? Now pick a small, no? Pick any distance from the wall. So give me a distance. 0.000000000001 millimeters. If we have enough n values, will we eventually get within that distance of the wall? So you understand the question now? Right? What about if I had 100 zeros and a 1? Is he eventually going to get that close? Yeah. We never run out of n's. So there's no limit to how close he gets to the wall. Meaning, if you had enough of them, if you had all of them, he'd get to the wall. If you had every single term added together, which is how many? An infinite number, then he would get to the wall. Do you believe it?
Yeah.
So, what does this sum equal? This sum equals 1. So, if you ever stop adding terms, correct, he's not there yet. But if you keep adding terms and you're able to do it forever, an infinite number of terms, then that sum will equal 1. He gets to the wall. Kind of weird, right? So this is a convergent sum. It converges. If you're able to imagine adding all infinitely number of those terms together, the sum will be 1. Now, cut it off at any point, then the turtle's not quite there. The turtle's not quite there. But take all the terms, which is an infinite number of them, and that series equals 1. Do you buy it? Okay, so that's a convergent series as opposed to this one that was divergent. Questions? Okay, how about this one? Okay, write out what it means in summation notation and as a sum, right? What it means in summation notation and as a sum. All right, Cole, how did this one go?
So 5 plus 1 squared over 1 squared plus 7.
Okay,
And then 5 times 2 squared, 2 squared plus 7, and 5 times 3 squared over 3 squared plus
good,
7.
right, excellent. So let's write that out. So he said 5 plus, sure.
1 squared.
So let's simplify them. 5, that'll be just 5 over 8, yeah. And then 20 over 11. 45 over 'Let's do one more. 80 over 'Okay? And on and on and on. Okay, so this one, in terms of saying, is it convergent or divergent? Well, we're getting to some kind of weird fractions, right? So let's go back and talk about the sequence, right? So this is a sequence. Let's just think about that sequence as a list of numbers. And you're all experts at sequences. Tell me about that sequence as a list of numbers. What about the list? All right, someone says it converges. Who said that? Trevor? Converges to 5. How do you know that? Yeah, so if you think of this as the associated rational function, 5x squared plus 7, we've got a rational function with the same exponent. So we can take the ratio of the leading terms, the ratio of the leading coefficients. So this thing goes to 5 as n gets big. Agreed? That's easy hopefully compared to lots of ones you did, right? That's an easy one. So now, let's think about this sum. So we add 5/8 plus 20/11 plus 45/16, okay? And so now, let's say we get out to end, dot, 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 meaning continue like this. Now let's say we get out to the millionth term. Millionth term is going to be essentially what? And then what about the million and first term? Essentially 5. So let's see. I'll put parentheses around it to say, so close to 5 that we'll just write 5, okay? But it's just a little bit different than 5. And then what about the million and second term? And on and on and on. This is a huge point. This is a huge key point. What about the sum? So the sequence is convergent or divergent? Convergent to 5, right? That list is going to get as close as you want to 5. Any amount of distance from 5, the small that you pick, eventually your numbers in your sequence will get within that tolerance. Okay? And now we're going to add them all up. Convergent or divergent? Clearly divergent, because if the sequence that those numbers are getting closer and closer to 5, then in the end we just have a bunch of 5, an infinite number of 5s essentially added together. Huge point, super important. Okay, So, what is it going to take for a series to converge, a sum to converge? If I have a sequence and this one converges to 5, I just end up adding a bunch of 5s together in the end. A zillion of them. It's just going to get bigger by 5 every time. What if my sequence converges to -1? My sequence. What about my series? We're just going to add a bunch of -1s together, and we're going to get infinitely large negative, right? What if my sequence converges to 0.4? Then we're going to add a bunch of 0.4s together. It's going to diverge. So what is the only possibility for a series to converge? Sequence converges to, has to converge to 0. So that in the end, we're virtually adding nothing. And then that sum will be a finite value. But if we're adding together a bunch of non-zero values in the end, that can't converge, right? That can't converge. See, the only chance that a series has to converge is if the sequence, again, does what? Converges to 0, so that in the end, we're not changing the sum, right? We keep adding essentially 0 over and over. So we're honing in on a finite value. So this is the principle of the divergence theorem. Given a sum, if your sequence does not converge to 0, or the limit doesn't exist, right? So if the sequence is divergent, or if the sequence converges to something non-zero, then that sum can't converge. It's divergent. So what is this? This is about analyzing the sequence to think about what the sum is going to do, right? That's what the divergence theorem is about. It's about looking at what the sequence does and to make a conclusion about what the series does. If that sequence goes to a non-zero value, or the sequence doesn't converge at all, end of story. Don't have to talk about that sum anymore. Okay, what about the flip side? What if the sequence converges to 0? Then the series must converge. Is that what that says? Does this statement guarantee that if AN does go to 0, then the series converges? Does that guarantee that? So what does this say? This says if the sequence does not go to 0, or if the sequence is divergent, then we can make a conclusion. Does that allow us to make a conclusion for when the sequence does go to 0?
Yes.
Mm-mm. So we'll find out. So if the sequence goes to 0 as n goes to infinity, then what about the series? Maybe that's true. Maybe it is true that the series that the sum is 0. But this statement doesn't tell us that. It doesn't tell us anything about what happens when the sequence goes to 0. It only tells us what's true when the sequence doesn't go to 0 or if the sequence is divergent. Then we know the series is divergent. All right, so it's an open question. Open question. All right, so let's talk about a geometric series. Geometric series. So it's exactly what you think it would be. What is a geometric series?
The sum of a geometric
sum of a geometric sequence, right? Which we've talked about. Now, it's a little bit different. So we're starting at n equals 1. So rather than it just being r to the n, we start with n minus 1 so that the first exponent is 0. Okay, so that's a little bit different. And then we also can have some coefficient a. So when we talk about geometric series, we make it a little more general than what we talked about a geometric sequence, right? A geometric sequence we said was r to the n. So geometric series, we say a r to the n minus 1. And so rather than the first exponent being 1, the first exponent is 0. All right, so I want you see this, think what? See this, think what? Write it out. See this. A is a constant, r is a constant, and n is our index that changes, right? A is a constant, r is a constant, and n is our same as it was before. So you see that? Think what? Okay, right here in front. Tell me.
I said A plus AR plus AR squared plus AR cubed.
She said A plus AR plus AR squared plus AR cubed. Exactly right. That's what that means. So we start with n equals 1, and we get a term according to that formula. And then we let n equals 2, n equals 3, and then add all the terms of that sequence together. Okay, so then the question is, for what values of r does a geometric series converge? Well, for what values of r did the geometric sequence converge? Remember? When did the geometric sequence converge? When r was? So all that stuff you learned about sequences, you have to retain it. You have to retain it, because everything, so we're going to use all that stuff in series. So the geometric sequence converged when r was between -1 and 1, right? When you kept multiplying a fraction by itself, you kept getting closer and closer to 0, right? And so that it converged to 0. All right, so what about a series? Is it the same results? Well, maybe. Who knows? We have to show that if it's true. So for what values of r does the geometric sequence converge? Okay, so here we go. So what we're going to do this is we're going to introduce something what's called a partial sum. So a partial sum so S sub n that's the sum of the first n terms of the series. So rather than add all infinitely many of them together, pick and say 7. So S7 is the sum of the first 7 terms, n going from 1 to 7. So Sn is makes sense, right? So it's part of the infinite sum. You stop somewhere. You stop after n terms. So it's not the whole infinite sum, it's just part of it. So we call that the partial sum. All right, so to figure out what r values, for what r values this converges, we're going to first write down the nth partial sum, which is going to be all these same terms, a plus ar etc. But now we're going to have a stopping. So the second to last one will be AR to the n minus 1, and then the last one will be. So that's how we would express the nth partial sum of this infinite series. All right, and then here's the trick. I'm going to take r times the nth partial sum. And what's going to happen? So what will my first term be of r times s of n? AR, right? But I'm going to start it here. I'm going to line it up with those. See, it's the same as this. So when I multiply A by R, I get A times R, but I'm just going to line it up with this one. Okay, and then I'm going to get AR squared. Oh, sorry. So this isn't right. The last one should be AR to the n minus 1, right? According to my formula. Was anybody thinking that?
Yeah.
Okay, speak up. If you thought that, you were right. So according to the way we express the geometric series, the nth term is going to be then AR to the n minus 1, not AR to the n. Now, when I multiply by R, the last one I get is AR to the n. Okay, did that change make sense? All right, so now what are we going to do? We're going to subtract. I'm going to subtract the left sides and the right sides. And what are we going to get? All these ones in the middle are going to go away, right? And so S partial sum minus R times the nth partial sum is going to equal what? A minus AR to the n. Okay, then I'm going to solve for, when I solve for the nth partial sum, I'm going to get, can I do two steps at once? I would factor out S to the n, and when I factor out Sn, I'm going to get 1 minus R. And I'm going to divide both sides by 1 minus R. So I did two steps at once. Is it okay? You see that? And then I'm going to write this as okay, and so what I can think about is that I can think about the nth partial sum itself as a sequence. If I let n equals 1, then n equals 2, then n equals 3, then n equals 4, I can think of the sequence of partial sums. So what would n equals 1 be? S1. S1 would just be A in the sequence, right? So if I make this a sequence, like this, would be what? A, comma, what would be the second term of the sequence? Careful. You had a Weber problem like this. Is it AR? What is the second term of this partial of the sequence? No, the second term would be S2. S2 would be the second partial sum, which would be A plus AR. S3 would be the third partial sum, which would be A plus AR plus, etc. So you remember that one in web work from a couple nights ago? So the sequence of partial sums means each one adds one more term of the series than the term before. So A, then S2 would be A plus AR, then S3 would be A plus AR squared, etc. So then what we have is that whatever this sequence does, converges or diverges, is the same conclusion about the whole sum. Because what is this sequence converging to? It's converging to the whole sum by continuing to add one more thing each time. Do you see that? So, little fact here, the limit as n goes to infinity of Sn equals the sum of An. So it's turning that series back into a sequence such that that sequence will eventually become the same thing as the series, right? You keep adding one more term every time. And so then that sequence in the end is virtually the same thing as that sum. Okay, so now we're going to analyze our result here in that way. We're going to analyze this result as what? A sequence of partial sums. And so what is it, what value of R then will make this second term converge? Right? When n gets really, really large, what will cause that to go to 0? Really? Just R equals 0? Yeah, so it's going to be negative 1 to 1, right? So we know that from the geometric sequence, if R is between negative 1 and 1, then that is going to go to 0 as n gets really big. And thus, this whole thing, because we'll go to 0. But what? Only if R is between negative 1 and 1. So then as n gets really, really large, this thing goes to 0, and what does the sequence of partial sums converge on? So as n gets really, really big, the sequence of partial sums, this will go to 0, so the sequence of partial sums will A over 1 minus R. And whatever the sequence of partial sums does, that's the same as sequence of partial sums, that's the same as the infinite sum. Okay? So when does the geometric series converge? When R, again, it's the same as when the sequence converges, when R is between negative 1 and 1. And what does it sum up to? A over 1 minus R. So not only did we find out when the series converges for what value of R, but we also find out what it converges to. Okay, questions on that? Does that make sense? Okay, so let's just include that over here. So this, what is this? This equals A over 1 minus R when? Right. What about, we had that special case when R equals 1, right? We had that special case when R equals 1. What about if R equals 1 for the infinite series? Does the series converge? What's going to happen in that series if r equals 1? What are our terms going to be? No, not quite. A plus, when r equals 1, guys. A plus A plus A plus A plus A. So when r equals 1, yeah, the sequence converges to 1. And then what happens in the series? You add a bunch of A times 1s together, or a bunch of A's. So in the case of the series, when r equals 1, it blows up. Okay, but if r is between -1 and 1, then the series will equal A over 1 minus r. So recall the turtle. What was that series? What was it? 1 over 2 to the n? That's all right? Okay. So we could rewrite that as 1/2 to the n, right? Is it a geometric series? Yes. Is it of the form that we've been working with? A r to the n minus 1? No, because what's the first exponent in the form we were working with? When n equals 1, we get exponent of 0. But in this, our first exponent is 1, right? So can we make this thing look like that? Can we get it to be 1/2 to the n minus 1? How can this be equal to this with 1/2 to the n minus 1? So how many 1/2s are multiplied together here? How many 1/2s are multiplied together? N. How many 1/2s are multiplied together here? One less, but I need n of them, right? If I want to make these equal, I need n 1/2s multiplied together. So what can I do? Just have one more 1/2, right? Now I still have n 1/2s multiplied together. I just split one out. I just picked one off. So I pick one off. Now I have n minus 1 left that I'm multiplying together. So I still have my n 1/2s. Okay. Now is this of this form exactly? Yep, exactly of this form. A equals 1/2. R equals 1/2. And what does this? Will this converge? Yes, because that's our r, and it's between 1 and -1. What does it converge to? A over 1 minus r, which is 1/2 over 1/2, which is, what was the sum of all the, what happened in the end? He made it a whole length of the hallway, right? He made one trip across the hall in an infinite number of days, right? And so this shows that that formula that we derived, the turtle walking across the hall, that was a geometric series. And we just used the a over 1 minus r to get the same result, 1, for that sum. Okay, so the next homework will be due Wednesday, but you're going to want to start this weekend for sure. I may add more on Monday, and we will have a quiz Monday. We'll have a quiz Monday.